So I just want to start with how many people here know about AI for materials discovery, and how many people know it in detail? As a result, I'm going to talk a bit in the beginning just about what that is, because materials is also like a super vague word that can mean many, many things depending on who you ask. I'll talk overviewing of the space, like why this is suddenly very hot and hyped as far as spaces, especially in the startup space, go, and then talk, what about we do, what we at altrove don't do, but also is very important for the space, and hopefully it'll give you a good overview. And please, if you have something that you want to ask questions along the way, feel free to do so. I think there should be enough time. I've hopefully budgeted this to last about 45 minutes, but we'll see. So, just before what materials are, why do they matter? This is like news articles from the last year. There's a bit of a shit show going on in terms of trade wars, particularly around rare earths. That's the most common thing. But ultimately, it's a very geopolitical problem at the moment. And that means there's a lot of incentive for people to innovate, particularly with industrial companies. If I look back, 10 years ago, there were maybe 2 countries in the world that had a critical materials or critical minerals pursuit program. Now about half the world does. And that's really like an indicative of how materials have changed. And now, okay, what is a material in this case? I'm going to use this example of an engine for an example of an EV engine. And I'm going to talk about materials that are used here. Ultimately, materials are substances. You can think of this table, but it could be, for example, an electric vehicle engine that are engineered for structure, for properties, for how they're processed, and ultimately the performance in a use case, right? And if I look at an EV, without having the high-quality copper for rotor windings, without having stator cores that are based out of silicon steel, without the other structural high-strength steel components, epoxies, and most importantly, the permanent magnet, this doesn't exist as a piece of engineering. And neodymium boron here, those are elements, samarium cobalt, are 2 of the primary methods that are used to make EV engines that are used in every electronic tool, from whether it's a power tool that you would use to drill something to a wind turbine. And it's, well, a lot of the problems and why do people care is because that is something that is only produced and refined in 1 country in the entire world. That happens to be China. And so it's often in the geopolitical tit for tat. But it's not the only example. In fact, I would say very, very many modern technologies that we depend on are a result of materials development specifically. This laptop needs to have a lithium-ion battery, otherwise it's not very carryable. But so is the same is true for an EV, for anything handheld, right? And that was the development of the cathode materials, the anode materials, the separators, the fluids that made that possible. That wasn't possible before the materials development. Same is true ultimately for modern semiconductors. It's a bit of a low blow, honestly, easy one to pick out, but this is dependent on extremely high quality processing methods for silicon. Any development below the 45 nanometer thing, which is basically the last maybe sort of 12 to 15 years of improvements in terms of reducing the size of semiconductors, comes from developing so-called gate oxides, in this case hafnium oxide primarily, but there are others as well. Jet engines, same thing. Hard drives, same thing. All of these are really engineering developments that are dependent on previous materials developments. And this means that, of course, new materials develop new engineering, develop new technologies, and are at the cornerstone of those. And that's why they are scientifically, but also industrially interesting. And I couldn't resist but put this in. Of course, it's a bit of an AI for science year at the moment. OpenAI wants to build an AI for science team. It's less than a year, although Nobel will soon be given again, since AlphaFold was the first really computational algorithm to win a Nobel Prize. Although, if you go to physics and the other parts of the Nobel Prizes last year were also given pretty much exclusively for computational methods. So there's a lot of interest in computational methods and AI for science. And I'm going to talk specifically about AI for materials in this case, and specifically like things that come out of mines and end up in electronics and magnetics that go into engineering products. And that's specifically what we work at altrove, but if I had to cover every type of material, we would be here for an eternity. Plastics, batteries, etc. So, why do people care about computational methods here? And the answer is sort of obvious. It's because the development is super slow, right? This is a very expert human-driven field where I design an experiment, I have an idea, I design something, I run something, I repeat, that takes a week. I do this for a couple of years, I maybe get somewhere, maybe I'm getting close to a result, I spend another 3, 4, 5 years optimizing, and then I try and scale that. And that's a 10-year process. That's often $100 million. It can be sometimes much more, sometimes slightly less expensive. But that's not a way that anybody can solve a problem. If I tell you, hey, I need to solve this problem, and you tell me, okay, give me 10 years and 100 million, there are very few problems where this is actually worth the balance. And so the kind of promise of the whole space is, well, let's shrink that. Let's shrink particularly the cost, but also the time, right? Can we do this in a year? Can we do this in maybe 99% less of cost? I think the answer is you absolutely can. And if I didn't believe that, I wouldn't, I guess, be CTO at a company trying to do that. But the hard part, obviously, is how do you do that? Which part do you innovate? And ultimately, how do you remove the human need or minimize the human need, not be limited by human and skilled individual development? And the answer is, well, I think the jury's out, but we'll know maybe in 3 or 4 years, I think. Just as a note, if you ever thought about building a startup and you like materials or you like AI for something, you could probably raise money on like 3 slides and just sounding like you know what you're doing. We raised, I mean, that number is a bit confidential because it's not out. But everybody on the slide who's listed is in like the top 2 or 3% of how much money they raise for what level of technical development that. It's a very research-driven field with people from all over the place. DeepMind, who kind of left the team there, OpenAI, etc. People getting involved in making AI for materials. But these companies actually do very different things, right? Because the goal is, and after this we'll get into the technical details, the goal is ultimately to take a set of engineering properties, right? I'm an engineer. I want to build a motor for an EV. Let's keep using the same example. And I want it to have a specific drive, ability to move at a certain speed with a certain energy density, and I want it to be super light. I can translate that into a set of magnetic properties for a material that if I have this material, I can make this work. But then that material doesn't exist, so what do? The goal is ultimately to go from a set of properties to a physical material that can be produced at scale, right? And obviously, this can't be done in one algorithm. Just as a note, there is no algorithm in the world which will do all of this in one session, one go. So we need to break it down. And I'm going to break it down into the 2 most sort of straightforward ways, I think, with a little intermediate that I'll go into in a second. The first one is what I would call crystal structure generation. This is generative, so think diffusion models, think variational autoencoders in some kind of generative form. And the goal is to figure out how atoms arrange in the right way to result in a specific set of properties. And when you do that, you can actually say, okay, this arrangement of atoms, if I can just make it, probably meets my need for what I need at the engineering and industrial level, right? It's not always true. Sometimes the arrangement doesn't matter. Sometimes it does. But, that's why no company here, and all those startups are working often on very different verticals and therefore different tech stacks. The second part, well, in some ways it's much harder, which is to how to generate the actual how to make something. Because if you can figure out how to make something very effectively, then you cut out what is perhaps 70% of the total time and probably 90% of the total cost. However, that's in some ways even more difficult, because what differentiates these 2 regimes, and I think this is being quite prevalent in the talks we've seen in this room, is the volume of data. In the first case, we're talking 5 million data points of very diverse, and then another 100 million data points of single snapshots, right? That's a very high data regime, relatively speaking, for the science world, not as big as proteins, but a big data space. The second one, we're talking maybe tens of thousands of data points, in sometimes very low quality, very mixed. And so the solutions that work in either side here are not the same. And therefore, the question for me is the left side is generative, the right side is more about representation learning, and how do we really effectively take general information from basically effectively to training or pre-training on unlabeled data, which can be something about structure, and apply it to be able to be very effective in a more active learning, sometimes even Bayesian optimization framework in the second half. Very briefly, crystal structure generation is not something we specifically at altrove do, but I think it's very, very important to talk about it because A, I think it's extremely interesting, and hopefully you guys will agree. But two, it's also really difficult. And there's a lot of work that can be done here. So the idea is we need to predict that arrangement of atoms. It's called a crystal structure. It's ordered. It's some arrangement of typically atoms in the inorganic case, but could be ions, could be molecules, that are solid and repeat in 3 dimensions infinitely. And that last bit, that repeat, is probably one of the hardest things about the space, right? Because if I'm now looking at that neodymium boron, that's in my permanent magnet in my motor, the arrangement of atoms looks like the central thing here. I don't have does this pointer work? No. That is the arrangement of atoms. The one on the right is a 3-dimensional reconstruction, so you can see what it looks like in 3D. So my goal is to say, I want to link that arrangement of atoms to the fact that it has really interesting properties. Or even better, I would like to generate that arrangement of atoms given the set of properties. But that, as you can guess, is relatively complex because I have to deal with a repeating unit. And I don't necessarily know what the bounds of my repeat unit are either. But let's be real, it can be done. And honestly, the advent and the hype is really thanks to DeepMind, where a paper called Scaling Deep Learning for Materials Discovery, also colloquially known as GNOME or Genome, was released in very late 2023, end of November, where the goal was, can we generate plausible and simulation-stable crystal structures, so arrangement of atoms, and can we do that at scale? Honestly, I don't think the pipelines are, in this case, were massively complex, right? You're doing some kind of graph network, you're trying to encode that, you're trying to be generative or somehow creative on that representation. Maybe you do a bit of random structure searching, you shove that into a validation machine, and then you see, is it stable? And example here are 6, but why it's interesting, well, there were another 600,000 or so. It says 400,000 there, they released a few more since. So 20,000 materials have been made in the history of humankind. In terms of physically being made, maybe another 20,000 had been predicted before November 2023, and in December 2023 the number was 600,000. And as you can imagine, that changes how you might build and how you might actually try and go about making materials in this space. And it just showcases one thing. Yes, we can generate. Now, if I'm going to be honest, and maybe this is a bit off the record, although I guess this will be somewhere on YouTube, most of what's in there is crap. Probably 80% at least, maybe 90%. That said, even if 90% of it's crap, it's still more predictions than had ever been made up to that point total. So the paper is really good. Most of it's crap. Now, there are obviously architectures to do this, and I'm just going to really summarize. I think there are 2 primary ways that people have tried. Microsoft, on the right, for example, released a model called MatterGen, where the goal is to just do diffusion, right? Basically build a diffusion model on some prior and figure out some kind of bounding box based on a composition, and then we're trying to replace and put atoms in there in terms of architecture. And classic noising, denoising process. I'll talk about why that is actually somewhat complicated and perhaps doesn't work as well as you might think in a second. The other ones are latent space work, right? So this is particularly work at MIT that's been really excellent on this side, but you effectively build some kind of transformer or encoder-decoder architecture where your goal is to take a structure, that arrangement of atoms, encode it into a latent space that is a little bit easier to deal with, doesn't have periodicity, doesn't have necessarily a graph, may just be a simple vector. And then you find ways and other constraints to diffuse or, well, be generative on that latent space, and then you decode afterwards. And just as a note, I think what MatterGen works and it doesn't. It doesn't work for anything complicated, and I suspect part of the reason is that it's going to be a bit of a strange slide here, but because you have an inherent periodicity, when you noise something that is periodic, you do not remove all the information from it, right? So the idea is that in a noising process, in a diffusion model, right, your goal is to noise something, take something which is nice and ordered, and your image, for example, and your goal is to pass it to nothing, something which has no information. And by learning this denoising, this noising process, you learn to denoise this thing. But if you have a periodic image, this is not true, because actually even post-noising, no matter what you do, you don't remove all the low-frequency information that is associated to the fact that you have a periodic unit. And unless you also somehow remove that, you don't get this. What's even worse, I mean, the differences here are minor, but if I duplicate my cell, so I take an atom, one of my sets of crystal structures, and I stack another one on top of each other, the structure is the same, right? So from a materials perspective, from everything, from simulation, from calculation, nothing has changed. I've just sort of defined my limits slightly differently. However, you want to noise it, your noise spectrum, even for the exact same circumstances, is different. So now we're not really building a one-to-one mapping here, or any kind of noising mechanism that we can properly learn. How do you solve this? I mean, I think there are two ways you can do it. One, you either change representation. So you find some way to avoid this by not necessarily a latent space, but some kind of transform. Obviously, we're periodic. The obvious thing is to do something FFT related probably to transform it to a less periodic representation, where hopefully now noising actually results in complete loss of information. The other option is to build larger and larger and larger cells and hope that, well, that you don't have to think about this unit cell. Let's just put in 1,000 unit cells next to each other and hope that we can figure out how to put 100,000 atoms in the right spot. That's very computationally expensive, though. So the question here is, I think this is one of the bigger open questions, and I think why generative modeling here is working, but it's not working as well as it could be. Now, I have to take a moment. I want to compare to AlphaFold a bit, because honestly, the problem is very similar. We have some people in the audience who know this far better than me, so if I say something unreasonable, please say so. I'm not going to talk about the architecture. I'm going to talk about this as an information problem, right? What is AlphaFold trying to do? It wants a sequence, that protein amino acid sequence, right? And some additional information attached to that that comes from, matching it to various other parts of it to itself and so on. And it wants to turn that into a structure. Now, that feels at first like a pretty complicated problem. Oh, please, if you want to take a seat, go. No, go. However, there are things that make this a lot easier from a pure information perspective. Firstly, there are only really 20 individual amino acids. Now, there are actually like 500, but there are only 20 that are common, right? And so actually my starting space is quite limited. Secondly, on the other side, yes, theoretically proteins can assemble in any kind of way, but they're primarily dominated by folds, basically ways that protein interacts with itself. And turns out, yes, there are about 1,500 of them, but they go into families which are much lower in terms of number, and as far as I can tell, no really significant, maybe except one or two families have been discovered in the last 15 years. We basically know almost all the folds. So really we're thinking of, we have a limited starting space, we have a limited final space, right? We know almost all the amino acids, we know almost all the folds, and we're trying to figure out how to go from one representation to the other. And that simplifies the problem. Now, if we think of this in comparison to the material science space, and the goal I'm looking at here is I have some composition, which is usually what you can vary as a way to make something, calcium antimony oxide. I also have a limited starting space. This is great, right? I only have, well, there are 118 elements that are generally listed, but let's be honest, about 60 of them are kind of nonsense, either too heavy to be ever present or horrendously radioactive. So I have about 60 common elements. So again, limited, right? This is great. Similarly, I have a similar feature to the folds on the other side. There is symmetry that must be followed by these repeating unit cells, and there are 230 space groups. There are no more, no less. This is like a set number. There are 230 of them, maybe 100 or so are very common. So again, I have some similarities. Then what are the real differences? The problem for me, the last problem, and that makes this maybe a harder problem than the AlphaFold side, beyond, I think, a lot of the work, the fact that people really spend a lot of time making this protein case work, is that there isn't a set number of or size of the result based on your input. And what I mean by this is that in protein spaces, roughly I have this many individual amino acids. I know roughly how big my final product is, because I know that each of these amino acids takes ever so much space, right? But let's think in the materials case, what's hard is that if I change this, 227, And I say, okay, I'm going to make a slight varied version of this. It's going to be 51, 49, 125. Now, theoretically, I need 225 atoms minimum to represent that, right? And suddenly, by changing my composition by 1%, I have changed the size of the output by a factor of, well, 22. That's problematic, right? Because it means that you have to somehow, especially because you have to try and guess usually. All the algorithms so far try to guess that repeat unit and then put the atoms there. You're having to guess that on very, very poor data, very, very rapidly moving space, and I don't think that has really been solved. So the fact that my output size is very random with respect to my input size, and sometimes even for the same input. For example, calcium antimony oxide has 2 different structures, if I remember correctly. One of them has 22 atoms in the actual arrangement. One of them has 88. The fact that I should be able to generate both of those possibilities from the same input is tricky, right? It's just a little bit harder in a way that I think, maybe proteins don't have the same thing. Maybe they do. I can't profess to be an expert on that. And sometimes judging something to be reasonable is really hard, right? This is another magnet. It's called a ferrite magnet. There are 2 atoms that are in black, and this is used industrial all over the place, and we have 3 elements that are very similar: strontium, calcium, barium, right? They're in the same group, so in the same vertical column in a periodic table. They behave about the same. Can they make this structure? Well, it turns out strontium can, barium can, and calcium can't, except it sort of can. If you have strontium and calcium and they're sort of randomly represented on those sites, you can go to about 30, maybe 50% calcium and it's fine. But now we have another issue, right, we've introduced, which is what I would call disorder, right? And that's the fact that actually real structures have what are called entropic effects. I have 2 atoms that sit on sites and they keep swapping. They might be in one cell, they might be in one place, one might be another, and it's random. And if I want to represent that in the right type of data that is used to train those generative models, I need to build very, very large cells, and that calculations haven't been done. So I mentioned this in a previous slide, but basically this disorder is not represented in the training data because it's based on a simulation called density functional theory. So I'm leaving out maybe half of my material space and saying, oh, that's disordered. Let's try and not deal with that. When that's actually extremely important for ultimately interesting materials and stability, right? And so there's a lot of data issues still to be worked out in this space. That said, it's super promising. It's very interesting. And if you have good ideas, you should try and work on it, because I think this is, whoever solves this is going to have a really, really great time. I think it would be as impactful in some ways as I'm sure AlphaFold was on the protein side. But one thing that I haven't mentioned, I think this is kind of, what do you do if you are able to generate these, right? Right now, you don't necessarily know if you make something whether it's interesting, right? And this is what I call screening. It's a sort of second part of this. And there's been a huge amount of work in the last year, and this is relevant, I think, to all chemistry spaces, chemistry, even the sort of biosides, and materials. There's been, I would say, the advent of something called MLIPs. I think that's more or less the established name now. Machine learning into atomic potentials. But what they do is, it's a graph neural network, typically, that takes as an input the cell, the arrangement of atoms and in it, and it tries to predict 3 things. The energy. The lower the energy, the more stable you are, the more realistic your structure is to actually exist. The stress on the cell itself, which is a tensor output, and the forces, which are at each atom a prediction of basically the force individual as a vector output on that. What's great about this is you might be able to think, oh, I can fine-tune and hijack these outputs. So if this is actually something, I don't think there's been many publications of this at all, but it works extremely well if you train this, you take it basically as unlabeled pre-training, and then fine-tune, say, the energy output to predict some property of interest. You need to obviously have enough data, maybe at least 10,000, probably closer to 100,000 data points, based on our testing internally, but you can get much, much faster. I'm talking 1,000x speed compared to previous methods. So the ability to now judge 1 million structures for whether they're reasonable or not, whether they might have interesting properties or not, can be done. It could not be done, I can tell you that 12 months ago. But this space is moving as a result very, very fast. And I think what's interesting here is this enables us to do tasks we haven't before. Now, architecture. there's a lot of work. This has been like a continuous battle between basically Meta, Fairchem, and a bunch of different startups to try and reach the best benchmark on something called MathBench Discovery. Honestly, best benchmarking website I have seen for any kind of ML modeling. You should use it as an example. Kudos for making it really goes to, I think, mainly one guy, Janos, who was at Berkeley and Cambridge earlier. And currently Meta is winning. But we'll see if that is the case. There's been a lot of work on basically you take an input, you do some embedding, you do your short-range, long-range attentions, the classic GNN stuff, and then you get to the prediction of the aforementioned three results. However, what's interesting is that I don't think there is an agreement yet. How should, for example, the model be equivariant? Now, most indicate people say probably yes. Now, if we look at AlphaFold, I think the answer should be probably no if you have enough data. But if you don't have enough data, maybe you need to be equivariant, for example, to rotation and translation. So these are often SO3 equivariant in practice. Something that came up, please do come in, I think a couple of months ago is, how do you predict that forces? The forces are technically meant to be conserved in a specific way by actually taking gradient with respect to the energy. That's how they would be traditionally computed in a simulation framework. But direct force conservation is actually much, much easier to train. Your training loss drops much, much faster. So surely you would want to be in that regime. Turns out if you want to use these models for any subsequent processing, you actually need the energy conservation, or you get drift of your final results. So this, I think, an interesting reflection where, for example, using some clever training scheduling, this model that's top here, ESAN, is basically performs best for a simple reason. They said, okay, we're going to choose to be energy conserving, and that means we're going to drop the force head, the third head there, and just calculate that on compute instead. But we're still going to train with it there. So we're going to do our first training run through that. We're then going to change training schedule, drop the forces, and do just a prediction based on energy conservation. And turns out this results in much, much better performance. Short and long range attention is really hard. You have an infinite number of atoms. You can guess that people like to think, I'll just choose all my atoms within 5 angstroms, right? This is not very far. And the short answer is, because most of these structures are ultimately stabilized by the fact that they have long range periodicity, that probably means that a lot of featureization is not yet caught in these models. To a lesser extent they are, because there's message passing infrastructures, etc. But a bunch of it probably isn't caught. So there's still work to do. And honestly, the biggest problem might be the data. And what I mean by this is, you need to be careful when evaluating, right? 100 million data points, excellent. But they're all simulations from a framework called density functional theory. And in this case, they're all at like 0 Kelvin. So that's as infinite cold, right? So not a single atom moves, atoms aren't allowed to move, everything is just stuck. Great, because the only way you can solve the Schrodinger equation. So compute-wise, otherwise you're screwed. Not so great, because you remove about half of all the effects of how actually materials behave, which are primarily entropic effects. There's also, as I mentioned, nothing disordered, because these simulations can't deal with the idea that an atom might be one or might be something else. So actually, even though the data volume is high, the data has bias, right? And that means that at least generation in this space, and all the generative architectures I've seen in this space, mimic biases of its training data. What do they predict? They predict unnecessarily ordered structures, which in reality would be disordered. What do they predict? They predict arrangements which are much less symmetric than most things actually happen to be in practice. And it turns out symmetry is just favored at high temperature because of entropic effects. So data, I think that this is something to take over in general. If your data has systematic bias, evaluate your results for it. Because at least here, as a material scientist, it's very obvious that results have the same systematic bias as the input data. But the question is, how do you make the right input data without consuming infinite amounts of compute? I want to just touch on something, because this, I think, in AI for science, there is perhaps sometimes a risk of overthinking compute without thinking what happens next, right? And it's sort of a tragedy that to this day, there hasn't been a mass market drug that was discovered computationally. You can't go to a shop, there's not a single mass market drug, as far as I understand, no, that has been computationally discovered. And why, right? We've had maybe 15 years of drug discovery and AI startups. Why haven't they succeeded? And the most common problem is that they predicted something which, when put into use at a later stage, didn't work for a property that they didn't predict. So the equivalent of this would be synthesizability. Like, okay, for a material, forget everything. It's amazing. It fits all the properties. Can you actually make it, right? Something we've done internally is spend a lot of time in figuring out how the hell do you measure this? How do you build the data for it? How do you judge it? Because it turns out that most predictions are kind of not very synthesizable. And so if you want to actually build a material, you need to judge that, and you'd want to judge that computationally, right? Because experiments, actually physically doing an experiment, they're expensive and they're slow. It's much better if we can do this computationally. This is, I mean, the result. I can't share the full model info because it's going to be out probably later this year. But for us, one of the things we did recently was build a mixture of experts model. Yeah, it's not the, honestly, there's work to do at the very end of this part that took embeddings or representation learning based embeddings out of these foundational models, out of these large MLIPs, combined that with really heavily encoded compositional informations. So one is tracking really understanding of the local atomic environment, one is tracking information about the composition. Those are pretty orthogonal. And then you put them into a mixture of experts to predict, and I mean, the results are more or less, for the most synthesizable candidates, more than half of them you actually can make. Just turns out that they'd already been made. That's the sad thing on this paper, but it'll be out. But the answer here is that this is one way that one should maybe, if you're in the AI for science space, think also in terms of what can I take from this, and how can I use representations as effectively as possible. And maybe last, this is the open challenge before I get on to the next stage. But the short answer is, how do we incorporate disorder, and how do we predict the outliers? And this may be underrated, but most interesting things that are made are outliers. This is an unfortunate thing, right? If something is really good at something, say as a material, well, we're going to optimize the hell out of it and find the best version possible. Turns out it's the best version. That just tells us that is an outlier. So actually, really, I would think of the AI for science space and materials prediction particularly as you are at your best if you are extremely good at identifying plausible outliers. But then you're always at the edges of your training data. So how do you best take away and separate an outlier from just a calculation error? Right? And that's a challenge. I think that's a really, really big challenge. Now, I think I have enough time. So I'm going to talk about recipe prediction as well. And as noted, the other challenge here, data. We're looking at maybe 30,000, there's probably about 50,000 reactions out there. That's your data volume limit. Only successes. Terribly notated. There's really, the data is bad. And there's not much of it. So we cannot do foundation model size modeling, right? Because data volume is not enough compared to the amount of basically amount of features and amount of weights you'd need. So we're left stuck in using a couple of different things. Active learning, ideally with representation learning, embeddings, constraints, as much as you can put them in. Fine-tuned MLIPs, right? So as mentioned, you can hijack some of those prediction heads and use them for different properties. This works if your data volume is maybe 5,000. This is my sort of personal rule of thumb based on our tests. 5,000 data points seems to be about right. I don't know if this translates to other fields, but that's the sort of kind of data volume where you can start to think of fine-tuning. And then more traditional MLIPs like XGBoost, etc. I think a bit less interesting. The problem is it requires a lab. So very briefly, we have a lab. That's part of the reason we built this thing the way we are, why we're tackling this part. Altrove, the short answer is we use a lab, but it's not the main reason or main development. It's everything algorithmically that attaches to that. So we're saying this is a structure. We can screen it. We think it's interesting. How the hell do you make it? Can we predict how to make it? And if we can predict how to make it, can we figure out how to iterate on that, like in an active learning context? And I'll share some interesting results about this, particularly regarding representation learning. But the short answer is you are massively improved in this space by having good representations that you can take out of much larger models. The hard part is figuring out how to best use them. For us, well, we're producing a lot of synthesis data. One day we'll have more data than the rest of the world combined. That will probably be in a couple of years. But that's also important because that allows us eventually to build larger models. That's about the company. As noted, we've done a lot of work on the synthesizability. I already discussed this, but really the idea is you take maybe 5 million structures, you keep reducing it by choosing this material is interesting, this material can be synthesized, this material meets an industrial need, and then you make it. And yeah, that's not so easy. You need to predict the recipe. You need to predict all parts of that. You need to figure out how to encode those recipes. You actually need to carry out the synthesis, and then you need to do everything post-synthesis automatically, right? If we're doing 100 experiments a week, nobody can be out there trying to analyze the results. That needs to be all automatic, which we also developed. Now, there's a lot of work here. I think it's really interesting that what can be done, the space is also moving fast, nobody knows what's going to work exactly. There's been agentic attempts, there's been compositional encoders, various ways to embed your information about a recipe. But a recipe is a very unstructured data format, right? It's like, add this with this. I mean, yeah, you can leave the adds out, obviously, in a chemical, but you're adding things to each other, you're describing atmospheres, you're describing mixing procedures, things like this. There's been some LLM encodings, seem to work. Sometimes you're looking for a simple one-hot encoding, surprisingly effective as well. And the answer is really, how do you best use information that is elsewhere about chemistry, about materials in this low data regime? And I think what's interesting, just to talk about this representation learning, is it does make things more effective. Asterisk, not always. Representation learning, for example, just to put some test results which are in a kind of a mess to this day, you can take a middle layer, intermediate layer model from one of these MLIPs, right, one of the CNN layers, take an intermediate layer, use that as a representation. Turns out, what does this do? If you need to move into a new part of your recipe or composition space, you actually can take data that you've already used and you have generalizability. So it turns out that you can actually generalize quite effectively by simply being able to take a very good representation. Now, I think the previous talk here just before lunch was talking about what's in distribution, what's out of distribution. My gut feeling, although I don't have proof, is that this is a way to bring more of the space in distribution. What's interesting is that it doesn't seem to make much of a difference in terms of the data points you need in terms of speed, right? So you might say, oh, we need to do 30 experiments and then we can iterate of those and do another 30 and another 30 and another 30 in a sort of Bayesian learning space. Based on our results, you don't get much faster in terms of the amount of data that you need by taking these structural embeddings. However, you get much more generalizable. And that means that if you now change into a completely different space, but you have some bits of similarity, you can do that. Some other works, yeah, there are various other compositional encoders. I want to actually add, since I almost forgot to say it, one thing that's really interesting, that representation is usually something like 512 or 256 in length. We've tested reducing it, intentionally compressing the embedding, and it seems to improve performance, weirdly enough. Not if you compress it too far, but you can actually usually compress these, and that seems to result in improved performance. Likely because my hope is you bring more of the overall space to be kind of, you have less dimensions that are irrelevant, right? Yeah, you have a much tighter and smaller space where less of it is inaccessible. Because obviously one of the dangers of going into an encoded space, an embedded space, is that you don't know which parts of the embedded space are actually physically accessible, right? So chemically, we know this, right? I can add element X, Y, Z, whatever amount, and the limit is always 100% of each one. This is a clearly bounded space. But in an embedded space, those boundaries are not necessarily obvious. You don't know necessarily exactly when you're at a limit and you're stepping into something can never be physically reached as a space. So it seems to me that at very high sizes of embeddings, this is a higher probability. You're often into parts of space where you actually can't access so easily. Whereas at smaller, slightly more compressed embeddings, you have less of that. If you compress it too far, say take 512, move it down to 10 dimensions, your performance gets really shit. And so don't go too far with it. You can usually do some kind of PCA to have at least a basic idea of how many dimensions you might want to pick. Usually it's probably something of, you can probably, I have a feeling for this chemical space, you can probably go down to about 50 fairly effectively. And lastly, I think this is honestly more an open question for me, something that we're working on, but something that's actually really difficult. How do you best encode a recipe, right? this really not very simple data type that has an indeterminate number of steps that you can keep adding on one after the other, after the other, after the other. How do you embed that for something like a GPU optimization framework? Because we're now no longer in an easy, you have to find some representation. I think LLMs probably have a part to play here of all things. You can build a bunch of priors, right? There's so many possible priors you can build by using various simulation methods, various graph similarity methods, many ways to find things that are similar, get priors, but how do you ultimately embed this space into some kind of optimization framework? Because saying I'm going to mix mill first and then put it in the furnace, for example, to take a literal example, is not very easy to write as a vector versus saying I'm going to mill, furnace, and then mill again. How do you differentiate these two as a vector? I don't really have a good answer for this, but we're working on it and we'll get there. So lastly, I'm going to come back, just a quick look at the big picture, right? This is one theory of how, and one way I think about how materials and AI works, right? The potential is massive. These industries are worth probably $1 trillion. If you discount steel, they're probably still worth 200 billion. And the point is that this is going to be disrupted, most likely, right? Like everybody's talking at the moment about how do very, very heavy compute, how can it disrupt everything in the physical world? What's hard is that while there may be large amounts of computational information for certain parts of the process, other parts of the process are very, very data low. And so the question is, how do we transfer information, in my opinion, from high data regimes into low data regimes? And really, it's not necessarily about removing the human, but making sure that no process is dependent and time locked by a human, right? If a human needs to jump in and it's at a stage where if they spend an hour a day doing it, your whole process runs super fast, that's fine. Eventually you'll figure out how to replace them. If the human is the limiting factor in all your processes, this is not fine. You will never be able to scale that process ultimately. And I think the answer is nobody here has figured out how LLMs fit in, by the way. There are some ways. People write embeddings with them. People use it to kind of try and find similarity papers. These are the low-hanging fruit. I think that the more interesting question will be, beyond sort of like fast data analysis, interpretation, adding some extra information for people to read, how do they really fit into what is very mathematical, very physics-driven data? Because I think if you can crack that, you again have access to another high data regime that you can bring in. And very lastly, I think in 2 years, it's probably 2 years to somebody succeeding. That's my optimistic perspective. And I think that whoever succeeds is one who manages to actually make novel materials by not having humans really involved or having humans minimally involved. And this really can't happen unless you can both generate and select really complex structure. Nothing simple. You have to be able to understand and use disorder because it's always going to be part of the optimization stage. This is really hard, and for materials, I think that isn't quite there. And I think it applies even to the chemistry side. And honestly, being able to get and generate both structures, but especially the recipes, because what you don't want to do is be dependent on sending some sample to somebody who will take 3 weeks to get back to you, and that be your iteration cycle. You can imagine if you're a software developer and you're told every time you make a small iteration, wait 4 weeks. This is impossible. So you need to minimize that time. And there's just an example, 3 examples of fun little samples from what we do when we make stuff at high throughput. And lastly, thanks to the organizers for inviting me, and also thanks to our team, which is small but very, very, very powerful in terms of across a wide range of disciplines. So yeah, now I think I'm reasonably on time. So thank you. And yeah, please, if you have any questions, ask.
Are there any questions?
I think there's, okay. Oh, go ahead. Looking this way.
Thank you, very interesting actually. And wanted to ask, what is the simpler problem? Not the recipe part, but the part about the structures. So let's say, just for an example, it might sound stupid, but might be that it's easier to, let's say, guess that ask the network or whatever model to predict that there should be an element from the second column of the periodic table instead of knowing that it's exactly calcium or something.
Exactly. So I think the generative approaches, I think, go from, I would say they go into 2 categories. There's like what you're saying there, like clever substitutional methods, right? A lot of work can be done with taking a structure that's known and doing some swaps in there, right? And figuring out how that changes, can you make that change, and how that affects the properties. I think this kind of work can be done. I think what's the difficulty here is people are really drawn, at least if you're coming from a pure computer science background, to trying to use the representation that is in those simulation data sets, in which case there is no ambiguity. The element is this type, right? I think there was one of the AlphaFold talks talked a little bit, Agustin who was there, talked a little bit about the fact that as different versions of AlphaFold explicitly or don't explicitly define some parts of the structure. And I think there is probably some kind of masked versions of this that could work in this sense. You mask some atoms and then you ask it to just generate, is this plausible given some things are masked? And maybe we can figure out what that mask part is there in the end. I think what's hard is that this is quite explored. Like a lot of people spend a lot of time in the 60s and 70s and 80s just like putting shit together and seeing what sticks. So what you really want to do is you want to predict structures where the unit cell, right, the crystal structure, that repeating part is different from anything you've seen before, at least similarly in chemical space. And that becomes a little bit harder in this sense. But yeah, it's a very good point. I think there's a lot of generative approaches here that haven't been exhausted. And probably partly because they couldn't be screened at high throughput until a year ago. So I'm looking forward to seeing where particularly academically this stuff goes in the next year.
Thank you for the talk. Yeah, I entered the room without any understanding of the topic. Now quite interested and excited. Thank you. So my question is about synthesizability.
Yeah.
So you mentioned that you basically want to predict how likely or how easy synthesizable the given structure is. My question is, like, where do you get or how do you collect the training data there, and what is the ground truth label here?
Yeah, so this is actually a great example because this is a PU type of world, right? You can only prove that a material is synthesizable. You cannot prove that it isn't, right? Because it just might be that you haven't explored the right way to make it, right? So yeah, you're stuck in a only positive, right, cases. What's useful here is there's something called the materials project here on the left, which categorizes whether structures according to their have been experimentally synthesized or not. So this is about 150,000 structures, which I think something like, I want to say like 20, 30,000 are positive, as in have been synthesized, and 120 or 130 are not, don't have this tag. Now, we use that as a test. We go back through materials project. We say, oh, here are like the top 6 structures within materials project that we can make. We make them. Turns out we made like 5 of the 6. And turns out they were all actually synthesized, but it's just some weird paper somewhere that didn't report it and it was missing. So there is data work to be done there, but that's how we collated this data set. So yeah, that's a very good question. It's a very interesting case of the PU case and that how you have to adapt kind of your ultimate model for that.
Any other questions?
Thank you very much for the talk. It was very fun and interesting. My question is, I guess it's related to 2 things you mentioned. One being the challenges of representing these recipes,
Yeah.
and the other being this high-level like concept of moving information from the high data regime to the low data regime. And I think those things are kind of clearly connected. So I was wondering if you have any like specific approaches or high-level intuitions on how you do that, I guess, for these recipes or just in general.
Yeah, no, I think that's very important. I think if you're ever in this kind of task, the best thing you can do is first build your testing data sets, right? So the first thing we've done on this front is both simulate, experimental, and collate trainings or data sets where we think, for example, we can test this. So there might be a data set of 4,000 reactions out there. There's like one from Omol, from the people at Meta, where they have some like structure or composition to functional property, like the thing you want to optimize relationships. And then what you can do is you can test, right? Some intuition. Structure and compositional components both are valuable, but they are very orthogonal. So what I mean by this is that information in each one is complementary. So when we were building this synthesizability model, for example, we had a compositional model, because the encoding here is easier. It worked kind of badly, because what happened is that it would identify like, oh, this is totally a plausible composition, and the structure was some like complete mess of arrangements that actually turned out that somebody had made the same composition but under a different structure already, for example. So we added a second source of information, which is the structural modeling, and suddenly the performance jumped considerably, and actually our experimentals went from like 0% success rate to 50%, right? I think I would aim to add more in this sense. I think it's given the data volume, like if you're under maybe 5,000 data points, especially under 10K or under 10K, I think it's mostly that you're going to be in an embedding space for the representation learning. So then your goal should be find as many different ways to represent that material, whether it be a compositional, take just the composition, pass it to a bunch of featureizers, encoders, transformers, get your final measure. Whether that be the structure that you can probably take from one of these MLIPs. And then the question is, can we find other ways to add more and more information? You do get more results by adding variety of information than trying to optimize each one, is my thoughts on that. And for the recipe itself, I mean, we started by doing a lot of data type definitions, like you have to actually build your own data structures first. Once you have that, this one I think is harder. Some current thoughts. You have to start by like taking the most varied parts of your recipe. Like if you don't change one process a lot, ignore it for the first, build a basic representation, build a test data set, which we have, and start testing. Some kind of one-hot encodings kind of seem to work, but honestly, I think they're not great. I will have a better answer for this in about 2 months once we've finished our tests on this. I think LLMs have a part to play here. The hardest part is like multiple steps. If you can just always add more steps. How do you represent that? I think you probably take all steps, maybe combine them in some way. Maybe something as simple as a sum. But yeah, I think that's the hard part. I honestly, this one is harder. I don't have a perfect answer, but we're testing, and probably in 2 months I can tell you.
Okay, thank you. Yeah.
Thanks for the talk. Just a quick question about what you think about quantum computing in your sphere, and like, are you exploring any opportunities, or how far is it of creating some real value in it?
Yeah, very interesting question. For context, I don't know if people know quantum computing well here, but the way it particularly applies to this task is the simulation is based on solving the Schrödinger equation. And quantum computers are extremely good at solving the Schrödinger equation under some variety of constraints. I think one of the things it'll do is it'll really improve that screening component. It'll make that faster again. So once we have a million structure, we can much more easily identify which ones are interesting. Otherwise, it's not quite mature enough. And honestly, we don't have the internal tech people who would know how to develop the right algorithms yet. But I mean, it's something I'm watching out for, but I think is maybe a year or two from impacting the space directly. Because you have to be able to measure it for a lot of structures for it to be really effective. So I think once it can do 1 million structures, I think it'll be there. Which probably is not very far from now. But yeah, it's interesting.
Okay. I'm curious if there are periodical structures, crystals, where the nodes are organic small molecules in the nature.
Yeah, okay, that's a very, very good question. I would say, I talked about inorganics, right? The thing you need to remember, that's like balls that are arranged in all sorts of interesting shapes, right? Now, the other part of this is small molecule generation, right? Small molecule generation in general is very difficult because if we go back, in my opinion, because if we go back to here, sorry, I'm gonna, this slide. Small molecules have like, you can just keep adding. So your in defined space, even though there's a series of rules, is kind of hard to define. You don't have as much limits. And on the outside, well, you can just keep building a bigger molecule, right? This is tough. Now, what you are talking is what you would refer to called hybrid materials, where you have mixtures of organic molecules mixed in with inorganic elements. The classic poster child of this is something called perovskite materials, which have been all the rave for solar generation for about a decade. They haven't still been commercialized. Who knows if they will, probably in part. And metal organic frameworks, or MOFs, which are also a couple of the startups on that space are specifically working on that, where your goal is ultimately to figure out the arrangement of organic components along with inorganic centers. You tend to build these really interesting mesostructures, so they look like cages. Like the kind of you get an inorganic molecule, you get like an organic thing, and they link in these all sorts of shapes and cages, which are great for particularly gas absorption.
But the MOFs, they are not crystal structures, yeah? They're just molecule, and they have some small inorganic atoms in the middle.
So I would say that what defines a MOF from a complex, so like a ligand inorganic complex, is the fact that it actually assembles into a repeating structure. So the framework part there, I would say that it's explicitly because it assembles into a repeating crystal structure. And I think it's very interesting because the one thing I would say the MOFs have going for them, the only property that matters is the shape, because they're used for absorption. So the only thing that matters is like, are there big cavities inside? And so that makes it a bit easier. But yeah, exactly there. I've not seen a generative model for them, but Orbital Materials, which is a startup in the UK, has specifically built force fields to try and be able to predict the geometry of these things. My guess is they must have done something generative. Whether it's worked, I don't know. They haven't published. But yeah, it's an interesting space, and I think it's in some ways harder because it's more complex. On the other hand, choosing which of them are interesting is probably easier.
Okay, I think that's it. Thank you very much for the talk.